Okay, just a quick video going over arithmetic sequences and series. Maybe in another video I'll go over geometric sequences and series, and hopefully infinite geometric series as well, because those are pretty cool as well. But anyways, let's first start off with an arithmetic sequence. So, for example, let me give an example of a sequence that would be deemed as an arithmetic sequence. So let's say we have 4, 7, 10, dot, dot, dot. So this is an example of a arithmetic series. So I just want you to notice here, what do you notice, like what's happening? Like we go from 1 to 4 to 7 to 10. And what is happening when we go from 1 to 4 to 7 to 10? What do you notice? What is the pattern? Okay, hopefully you sort of figured it out. So we see here that it's plus 3, plus 3, plus 3, and this is just gonna keep happening. So there is a what if we had to write like a rule here? Now, since it's an arithmetic series, the rule has to be a linear rule. Like it has to be in the form of a linear function. Now, in terms of geometric sequences, if you've heard of them, those are those are exponential functions. So, anyways, how can we write this? So there's a formula which states if we have a sub n, that equals to a sub 1 plus n minus 1 times d, where d represents the difference between each of these. So in this case, our common difference is 3. In this case, a sub 1 means our first term in this arithmetic sequence. So if we plug in the values here, we would get a sub n equals to 1 plus n minus 1 times our difference, which is in this case 3. And then we go from there. So then a sub n equals to 1 plus 3n minus 3, right, using distributive property. Then we would get a sub n equals to 3n minus 2. Now how can we check if it works? So let's plug in 1 here. We get 3 times 1 minus 2, and we plug in 1 in for n. Now you can sort of think of this as function notation. This is just sort of like, you could think of this as a of n. This is another way of saying that. So we plug in 1 and we get a sub 1, which is our first term in the arithmetic sequence, that equals to 1. Or let's say a sub 3. A sub 3 equals to 3 times 3 minus 2, or in this case, a sub 3 equals to 9 minus 2. A sub 3 equals to 7. In this case, this is 1, 2, 3. Now, even though we can still find terms that are not listed, right, or that's not listed in front of us, right? We know that it keeps on going and going and going, right? So in this case, we could find like even the 27th term, if you want to say that. So a sub 27. Remember, when we say a sub n, that also, you can that implies of a of n. If you think of it in function notation, it's the same thing. So we know that this is the formula. We just plug and play here. So 3 times 27 minus 2. So then that's just 81 minus 2, which is just 79. So hopefully you get the gist of what's going on. So our 27th term has to be 79. So that's how we define an arithmetic, or that's just an example of an arithmetic sequence. So you just have to have a common difference, and that's just where your number sense comes in. Oh, do you see, like, what is happening between the terms? Oh, it's increasing by 3. In some cases, it will be decreasing by a certain value. So this is just an example of a arithmetic sequence. Okay, so now let's talk about arithmetic series. So, a common just sort of thing to understand here is sometimes you will see a symbol that looks like this. You're probably like, whoa, that are those like the cool symbols that they use in calculus? Yes, this is the sigma notation or summation notation. This symbol is used in calculus, but it is also used for just summations in general, right? This implies to find the sum of something. Okay, just understand that. So, just some key things here. Let me just rewrite the sigma notation here. So, basically, on the bottom, for example, usually some number here like n equals to 1, right? So this would imply this would be our first term. And then the top would be the total amount of terms. So in this case, if we had an infinite like geometric series, we would put infinity here. Or in this case, if you had like a finite geometric or arithmetic series, we could put like 301. This is the total amount of terms we need to find the sum of from 1 to 301. And it won't always be it start at 1 though. It could be like n equals to 5. So in this case, what happens here? Basically, so for example, we have n equals to 1. We want to find the sum of, let's make it easier for ourselves, 51 terms. Okay, and well, what do we do now? So that's where our sequence comes in. So in this case, we created a sequence of a sub n equals to 3n minus 2. Well, if we put that sequence here, well, we need to find the sum of all terms from like 1 to 51. So like for example, if we do this implies like 1 plus 4 plus 7 plus 10 dot 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 all the way to, I just picked a number of plus 51. So all the way to 51, we want to find the sum of that. So there's a formula which states the sum s sub n equals to n over 2 times a sub 1 plus a sub n, where n over 2 means, yeah, the total amount of terms, right? So 51 over 2 in this case, and then that times a sub 1, which is our first term, plus a sub n, which is our total amount of terms. So just another thing to mention here, just sort of to see like how is this formula defined? Well, there was a mathematician who's known as Carl Gauss. So the story is quite interesting, actually. So his teacher, I think, as a punishment, gave him the challenge of finding the sum of numbers, including like from 1 all the way to 100. So his teacher thought that, oh, if he does 1 plus 2 plus 3 plus 4 plus dot 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 all the way to 100, that would take him a while, but he was actually able to do it in like a matter of minutes, because he developed a formula called n times n n times n plus 1 over 2. Sorry. Yeah, so this is the formula he developed, and this formula is basically implying the same thing. So thanks to Carl Gauss here and his wonderful discovery, which really is a game changer, we are able to find summations in much more efficiently. So now let's just plug and play here. So okay, n over 2, total amount of terms, so 51 over 2 multiplied by our first term, a sub 1, which in this case we can just plug in 1 here. 3 times 1 minus 2, which in this case is 1. Now again, we could have just went back here, but we usually just have this given to us. I just chose the same one. So 1 plus then a sub n. So in this case, actually, we plug in, when I said a sub n, our total amount of terms, what I meant is we plug in 51 in for n. So sorry about that. So we put then, so 1 sorry, plus then 51 in for n. So 3 times 51 minus 2. So then we will get 153 minus 2, and then there's just 151 plus 151. So now we just have 51 times 152 over 2. And now I'm just gonna put that in my calculator. No, we don't actually. Yeah, we don't. We 70. I'm just gonna throw that into my calculator. It's really late at night, and I just cannot. I have COVID. It's late at night, but I gotta make these videos somehow. So yeah, this is definitely doable without a calculator, I hope. Sorry, that should not. The screen looked weird for a second. Probably sorry about that. There we go. 51. Yeah, sorry about that. Yeah, that's just, yeah, we could have just done then 51 times 76. Yeah, we could have done that as well. Sorry about that. Oh my god. Anyways, yeah, 51 times 76. Yeah, that's just 3,000. Yeah, 51 times 76. So we should get S sub n equals 3,876. So the sum from 1 to 51, with the sequence 3 and minus 2, think about it here. All these terms, plus, 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 all the way to 51, we found it in a matter of maybe like about a minute or two using Gauss's formula. So just something to think about. Anyways, sorry I was just not able to do the mental math there. Just acknowledging we could have done 152 divided by 2. I don't know why I had to pull out a calculator. Of course, for the 51 times 76, that would have taken a little longer. It's better to use a calculator. But yeah, I could have definitely done the mental math there. Anyways, thank you guys so much for watching, and I'll see you guys on the next one.